I think I'm just gonna start. It'll be a while before the introduction anyway. Um, Hang on. All right. Well, hello everyone. Welcome to the second day of prologue or of this multi-agent systems course. Let's just take a look at the planning while waiting for the rest to show up. So, today is the second session, of course, and the first thing we're gonna do is go back to recursion and try again at understanding it. I wrote down I would do a live demo today. I think I'm gonna do that tomorrow actually. I think for the practice, like today we'll just mostly look at examples and try to really understand how it works. And tomorrow we'll really practice making it ourselves. And that also gives you guys the chance to practice it by yourself after the session, which would really help in making tomorrow more useful. After that, we're gonna look at the prologue exam. Um, So we're going to do the exam questions from the previous exam, and then we're going to look at the agent and environment theory, which will be short, and basics of Marble. Um, yeah, I'll wait a couple more minutes because it sounds like a really bad idea to start doing percussion without everyone here. Oh, right, of course. The bar here is only showing half the people. It's already 10 people in here. All right, I guess we can start. So, um, yeah, to everyone who wants to, the request to turn on your cameras again. That helps me a lot to have to teach if at least some people have their cameras on. And yeah, that's about it. Everyone clear? Everyone ready to start? Everyone able to hear me? Yes. All right. Just making sure that there's some that you guys are still alive. Okay. Well then, first we're gonna do is look at lists because most of the recursion in Prolog will be about lists. Just like most of the for loops in Python are about lists as well. Um, so um, in order to make good use of recursion in Prolog, we first need to learn about lists. So the way you write down a list is similar to Python. So you just have square brackets with values and commas in between. These can be any atoms. It doesn't matter which type of atom it is. So numbers, words. Uh, but of course, usually you'll be using the same type of value. In Prolog, lists are usually represented by head and tail. So if you have, we don't have um, names of lists, so you cannot put a you cannot have a variable with a name that contains a list that you can access from anywhere, just like in Python. Instead, you have a variable that contains the list, and in order to get specific values from the list, you split it up into a head and a tail. So as you can see in this example, um, By splitting up into head and tail, the head contains Volvo, just the atom, not in a list format, and the tail contains the rest of the list. You can also have multiple heads with this syntax. I see here that I have a comma too many. Hang on. So there you go, just one comma. Um, yeah, and even if the tail is only one element, it stays a list, and even if it's zero elements, it's an empty list. Um, and we do this because we do not have indexes in lists in Prolog. We can only access the first or the head of the list, or however many heads you have. Any questions about this? If you do, please write them in the chat. You don't get the multiple heads. All right. So say you're going through a list and you want to get two elements at the same time. You have to split up. You can only split up um, the the list once per recursive step. What I mean with recursive step, we'll get to that in a minute. But if you want to get the two first elements of the list for whatever reason, then you need to have two heads. So that's why we have syntax for splitting up into multiple heads, so you can access as many first elements of the list as you like. Um, I think if I go to if we see how to use a list in a recursive function, then you'll understand what I mean. Yeah, so the example with the next slide. All right, so we have an example, a rule that calculates the sum of a list of integers. Now this looks maybe a bit scary considering yesterday, but we're going to take a very in-depth look at this function. So I'm going to show how it runs in a bit, but first let's take a look what we're looking at. Um, the base case for this function says when it's an empty list, return 0. The recursive step says if the input is a list, well, the input should be a list, split it up into a head and a tail. So now we can access the head using the variable h and the tail using the variable t, and then return your answer in the sum variable. So this one is left of the list to the next recursive step, and that keeps going until it returns a result. Once it returns a result, it says the sum is the head plus the result. And when doing the recursive step, it only passes on the tail, not the head, so that the list actually gets smaller. Now let's see it in action, because just looking at it doesn't make it much clearer. And we're going to go through this step by step. Where do the heads get stored? The head is stored in the variable h. So when you call a rule, as you can see on the right here, you're calling it with a list as the first argument, and um, that list gets split up into the head, which will be 1, and the tail, which will be the rest of the list. What do you mean the second time? Yeah, yeah. So we'll see how that works in a bit, right? So if I call the rule, I'll say sum one of the list 1, 2, 3, 4, return it in X. So I leave X empty so it Prolog can instantiate X with that variable, with the result, I mean. All right, so what is Prolog gonna do? It is going to look for a match for this query. First looks at the base case. The base case does not apply because in the base case we are specifically asking for an empty list. You can see that because there's no variable inside of the list, inside of the square brackets. So this base case does not apply here. So instead, it's going to go to the recursive step. Now H in the recursive step is 1, and a tail is a list 2, 3, 4. Sum is empty because we passed on an empty variable. Um, Now, what does the rule do? First thing it does is call the sum again, but this time with the smaller list and an empty variable once again, because we made a new variable here called r for result. That's all it has done so far. So now we can move on to the so we need to do another recursive call. Everyone clear so far? So we called the rule and it has done one recursive step so far. Tell me if I'm going too fast. So the next recursive call, so in this recursive call, it's going to do the same thing again. It's going to look at the base case does not apply. This time the head is 2, and the tail is 3, 4. X, the sum I mean, is still an empty variable, because the previous recursive call also called an empty variable. And the first thing it's going to do is call another recursive call. So we're going to go, this time it calls it with not beautiful handwriting. Another empty variable. There you go. And it's just going to keep going like this, as you guys can hopefully see. So this time, head is 3, tail is a list of just one thing. So it's just going to keep going regression until it reaches the end of the list. So the sum is 4. And then in this call, in the last call, something special is going to happen. So once it passes on, if you go back one step, this one, the head is 4, and the tail is empty. So once we go to the next step, we'll see that it actually triggers the base case, right? Because it triggers the base case, it actually returns a value for x. So remember how instantiation works when doing search? We say, can you match this to anything in our knowledge base? Yes, it can. It happens to be able to match it to our base case. If it instantiates x for 0, which is possible, so it returns x is 0. Now let's look what happens to the previous call, because this is the one that called it. This rule called this rule. This rule returned x is 0. So what this one was doing is it had 4 as the head, an empty list as the tail, empty variable for the result. In the rule body, the first thing it does is call the sum of an empty list with an empty variable called r. This r gets instantiated for 0, and this is the first call that actually succeeds and actually returns something. So all these calls are still waiting. The, each one is waiting on its successor. So the first one is waiting for the second is waiting for the third, and only the fourth one actually makes a call that immediately returns something. So it made this call, which triggered the base case and returns 0 in this variable. So now r is 0. We instantiated it. Now it can continue. It says sum, not the rule, but like this empty variable here, is head, which is 4, plus r, which is 0. So the sum is now 4. So now this fourth call, can also complete and return its value. For its predecessor, so sum 3, 4, this one's also this one is getting results from the fourth call. And the result it gets in its R is 4. Um, so if you go to the next slide, so this call says x equals 4 because that's what it returned. So its predecessor, so sum uh, 3 as head and 4 as tail. What it did is it called sum of 4, which by now finally returned a value in this position. It instantiated R for 4. So now this one could also continue. Could say sum is head plus tail. So its head is 3 plus 4, which is I said tail, I meant the R, so the result of the successor, which is 7. So it instantiates its result for 7. And now this one can also continue. It can add 2 to this 7, which is 9. And so once the base case has triggered, as you can see, suddenly all the recursive calls start to succeed. So they all have to wait until the recursive call reaches the base case, and then it can go all the way back and actually return the value for each rule, for each query. So this keeps going until it reaches the original query that we actually called. And that will result in it returning 10. So again, this one, the head was 1, the tail was 2, 3, 4. Just write the sum name, right? Um, X is the one we're asking for it to return, right? So it calls it does a recursive call, or it did a recursive call. It said, bring me the sum of 3, 4, 2, 3, 4, and put it in R. This one, by now, as we just saw, did more recursive calls, reached the base case, came back, and said, your R has a value of 9. So instantiates R for 9. It took it a while, but it finally did it. So now this original rule can do its own computation. It says sum is 1 plus 9 equals 10. So the answer finally is 10. And that's how we, with this rule, can input a list of numbers, and after a bunch of recursive calls, it will return the correct answer. Were you guys able to follow this? Are there any questions? Kinda. It's a little vague. That's understandable. What does the R stand for again? Well, you can name the variables whatever you want. I call result. So the result of its subquery of its recursive call. Where did you get the one from exactly? Um, so when you call this rule, it splits up the head from the tail of the list. So um, the one gets stored in the head in the H, and a tail receives the rest of the list. It passes the tail on to the recursive calls. The recursive calls complete, and then yeah. All right. Um, I think it's a good. I think it will be good to continue because after all, this only really makes sense if you practice it enough. So, um, right. Let's try to do it. Try to work with it ourselves. So the task is modify the sum to do multiplication instead of addition. So this is the original sum rule. And the question to you guys is how do you change it to make it multiply instead of uh, do the summation? Small hint, you need to change two things. So the approach would be you start with the base case. Do you need to start anything and do you need to change anything about the base case? What should it do or return when it reaches the base case? And for the body, well, what do you change in the body? What should be different? Right, so you definitely change the name to multiply. Change 0 to 1. Yep. So we'll see in a bit why that's important. So what do you change in the body then? H times result. Yeah. So you change the plus to a multiplication. All right. So that is indeed correctly how you modify this function to make it a multiplication. Um, I tend to change the names of the variables a bit, but the names of the variables don't matter a whole lot. So yeah, because at the end for multiplication, it is okay to return a zero, but for summation, but for multiplication, you have to return a one because otherwise it will um, multiply every result by zero, which will always return zero. And of course, change the multiplication to a summation to a multiplication. Right. So um, ideally, you guys would try to do such a query manually by yourself. So a very good way to understand it is if I say I query multiplication um, of 2, 3, actually that's enough. So just 2 and 3, and then 1. No, not 1, the x. So if I say a query multiplication 2, 3 of the list of 2 and 3, and then return the answer in the variable x. Um, how about you guys try to go through the steps of this what's it called? This recursive rule, just like we did in the summation example. So what will be the next query? What will be the query after that? And what will be the final answer? Hang on, just oh wait, I'm just messing with my slides with my tabs a bit. So, were you guys able to go through it? So what would be the second query it asks? What would be the subquery? What would be the recursive call?
So the second query it would ask would be mul3x, right?
Yep. Oh, where did my pen go? I had the pen selected. All right. And then what will it do after that? Right. It will go to the base. It will call it without anything in the list. I see a question in the chat. I don't really understand the base case. So the base case tells the recursion when to stop. Whatever language you go to, because other languages can also do recursion, every recursion requires a base case to tell it when to stop, just like the while loop needs a condition for it to know when to stop. So what this base case does is give it its initial number to work with. So when doing addition, we start at 0, and when doing multiplication, we start at, well, we just start at 1 because we can't start at 0, because we would always get 0 if we start at 0. So once we have our initial number, which we get at the end, um, then we can do the rest of our calculations. And the reason it's called the base case, or well, the reason it's the first thing, is because when Prolog does a search and it does it in order, if it finds a recursive call before it finds the base case, it will never trigger the base case, and the base case will fail at stopping the recursion. Um, and so yeah, what the base case says is if your list is empty, if it's not empty, you just continue. You ignore the base case. But if the list is empty, return 1 as the result, and that gives its initial number to work with. Does that help? Does that clear it up a bit? All right. Um, yeah, so I'm seeing some correct answers in the chat. So, um, yeah, this one will result in the base case, so we'll return one. This one will then do not free. Remove that. This one would then return 2 times 1, which is 2, and that will cause this one to do 3 times 2, which is 6. And that's the final answer. All right. So how should you actually go about making a recursion rule? It's one thing to understand one, it's another thing to make it. Um, so before we start, this really requires practice. So you're not going to be able to learn it in 1 hour. Like it's actual skill you need to practice, and it's we're gonna practice it tomorrow, and I'm gonna ask you guys to also practice it at home today. Or well, you already are at home, but like after the session. But to give you some tips on how to make one, this is my approach. So it's the same approach we used yesterday, but this time written down neatly. So first, you solve the problem on paper. So if you had this list and we had to calculate the sum of it, how do you do that on paper? And we don't use Prolog, but we do it with a Prolog mindset. So we don't think of it like Python, where you just say use the sum function, but we actually think we can only access the first um, item in the list at a time. And once we have accessed the first item, we have to reiterate the entire function again to continue. Once you have done that, you go to think about how to do the base case. Again, I keep saying how important the base case is. So when should the rule stop doing recursion? Usually when reaching the end of the list, but depending on what you're trying to do, not always. And for the third, try to replicate your actions in Prolog. So um, whatever you just wrote down on paper, try to replicate that process in Prolog. And this is not a hard guide. This is just how I do it. And step one and two can also be reversed. So you could start with step two instead of step one. Depends on what you're doing. So let's look at an example. All right. So this one we're going to do together. So our task is find the kth element of a list. So we receive a list. We receive a number k, and then we have to, which would be our index. We have to return the correct value as uh, as the third variable. So in this one, we have a list, we have a k, we need to find that index in the list, it's the third index, and we have to instantiate e for this third element in the list. So our first step will be trying to reach the sample output on paper. So what do? We say we start with a full list, and our k is 3. We iterate, we take the head off, and then say, okay, now this is our list, and we only need to find the second element. Then we iterate again, take the head off, and say, okay, now I only need to now I need to find the first index. The first index is 3, which is now the head, which is now reachable. And since we can now directly access the head, this is probably when we will stop doing recursion. Any questions? I did go quite fast here. All right, so sounds like this is still understandable. Um, yeah, I get that you wouldn't be able to think of it yourself. That's why it's really important to practice. One more time. All right. So we have a list of 5 elements, and we want the third element. In Python, you would just say index 3, or, well, 2. But in Prolog, we cannot do that. In Prolog, we can only access the first element. We can only access the head. So we need to take off the head every time to make the list smaller until we can reach the element we want. So what we do is when we separate, so the list is 1, 2, 3, 4, 5. When we separate it into a head and a tail, the head would be 1 and the tail would be 2, 3, 4, 5. So we can still not access the element we want. So, but now the element we want is in the second position. So we iterate and say, okay, this time we do the same thing, but with this we pass on the tail instead of the entire list. So now the list is 2, 3, 4, 5. We take off the head again, and now we're at 3, 4, 5. We take off the head again, and hey, look at that. That's the element you want. All right. So the question here becomes, when do you stop doing recursive steps? When you reach your base case, right? But we've tried to figure out what the base case is. Um, Once it reaches 0. Yeah, so or 1. It depends on how it both implementations work. So I would say when it reaches 1, but you could also implement 0. It depends on how you make it. Um, but yeah, so once this number, remember this is our k, so this is the element of the list that we want. Once it reaches 1, we know, oh, the element we want is at the head, so that we can access it. So our base case therefore becomes something that allows something that returns the head once we have k is 1. So you go to the next slide, right? So when k is 1, it should end, and when that happens, we should return the head, because when k is 1, the element we want is in the head. So our case becomes, if we have a list separated into head and tail, if the k is 1 and the n is empty, instantiate n for the head. So this head will get copied into the n. Remember, n is our result. Clear so far? Or clear how this base case works? Okay, very nice. So now is the third and probably the hardest step, thinking of the recursive rule. So we took off one element and reduced the k, which is the iterator, by 1 every time. So, and then, yeah, then we pass on the rest of the list to the recursive step. So, any plans on how we might be able to do this? So just to give you a start, uh, the rule looks something like this. So we have a nicely written head and tail. We have a k, which is some number, and we have the n, which is the result. So what we want to do is reduce this by -1, or reduce it by 1, and pass on the tail. And we want to do that every time we do a recursive step, and then we trust our base case to stop the whole thing once we get to a point where we're done. We pass on the t to the next recursive step. So um, every every step of this rule takes off the head and passes the tail, which is the rest of the list, along. So, any ideas? All right. Seems uh, still quite challenging, which makes sense. All right. Well, what we do is um, right. So our goal is to call the function again. So at one point we want the cave rule. We want to pass on the tail. We want to pass on k minus 1 because it has to reduce the index that we were looking for. And we just pass on the empty variable again. However, as we saw yesterday when doing rules, this does not work because Prolog does not evaluate arguments. So um, let's see. One person is saying k is k1 k minus 1 in the thing. Uh, I don't think you can actually put operators in arguments either. I'm not sure, but I don't think you can do that. So what you would do is make a new variable, and there you say, yeah, I already see a correct answer in the chat. That's really nice. Well done. Um, so yeah, you have to reduce the k by -1 before you actually call the recursive step. And then here you can call use that new iterator. And so that is indeed the correct answer. So to go over it again, what does this rule do? In the base case, it accepts a list with a head and tail. If the iterator is 1, then put the head into the result. All right. What does the recursive step do? It receives a list which has a head and a tail. It receives some number here. Calling it n is kind of that's how you usually say some number, but it doesn't matter what number it is for now. Just like some I don't know, five, five or something. Um, and it receives an empty variable. What it does is it reduces the k by -1, and it saves it in k new. So k new is then 4, and it calls the function again, the recursive step, with the tail, the new k, and an empty n. When this returns, it will actually put something in this n. And when it returns something in this n, then this gets, so this original n, because we didn't change the names, gets instantiated for the answer. Now, since we don't have, I still have some new things to cover. Um, I'm not gonna go through the whole process of how this function works again, but I will ask you to make an example for yourself and just run through it on paper how this function works after the session. So just like we did with the sum, just go through every recursive call, what kind of query does it make, and what does it put in all those variables. It will help a lot. Um, a task here is to find the last element of the list, but we're also going to leave that for after the session. So this is going to be homework for the audience. Some random tips um, that I'm not sure how much they'll be useful, but hopefully there'll be some a bit useful. So first one, start with the base case. When should recursion stop? I keep repeating it, but that's really where you should start. You can have multiple base cases, just like you can have multiple versions of the same rule. Should the recursive call come first or last? So is it tail or left recursion? If the recursive call comes first, it means you assume it already returns the answer. So this one is a bit unintuitive, but that's because recursion is unintuitive. Um, when you go to something like this, something like multiplication, um, when you write it, when you write the rule, the first thing you're saying is, all right, I'm assuming I'm already getting the full answer from here. So all I have to do is um, multiply the head with the full answer of all the other ones, right? The order of in which you do things is kind of weird. If that's if saying that only confuses you, then forget about it. But that's the way it makes sense to me. And then tail recursion. Um, so tail recursion is a big thing in Prolog because it makes recursion more efficient, which is important because uh, because recursion is really not that efficient, and anything that helps making more efficient is helpful. And you can use accumulators to um, rewrite a left recursion into a tail recursion. And what are accumulators? That's our next topic and our last topic for recursion because I've had enough of it for today. So yeah, it is often asked to turn a left recursive rule into a tail recursive rule, and it often requires an accumulator. So what is an accumulator? It is a extra variable that accumulates values for your answer during recursion. So when we were doing the summation, you saw that um, the answers were saved in the stack. So the stack of queries is where you would save your answer. And you would not do any multiplication or addition until you reach the very end. And then on your way back, you do the addition. What accumulators do is they allow you to do the addition on your way to the base case instead of on your way back. And uh, because you're doing the addition on your way to the base case, by the time you're at the base case, you're done. You don't have to go back. Um, we'll see an example of this in the next slide. One more thing, it usually comes with an extra rule that initializes the accumulator for you. So, um, so the accumulator is an extra variable in the head of the rule, People don't like making accumulators themselves, so this usually comes with an extra rule that makes it for them. Question in the chat. So is it more efficient? Yes, it is. All right. We'll see an example. So rewrite a sum to use tail recursion using an accumulator. So um, we'll have the, I think I'll call it the constructor. So this one is what our user, the person who wants to use this rule, actually calls. He says, I have a list and I want to return a sum. What this rule does is, okay, I'll do that, except I won't. I'm just going to call another rule, sum accumulator. The A stands for accumulator. And this variable here is the accumulator. So it starts at 0 because when doing addition, it starts at 0. And this is the actual rule that's going to do everything. So it's a different rule, as you can see. We're not going to use the sum, we're going to use the sum accumulator. And all this first one does is take this rule and turn it into a free argument rule. So all the base case does is um, when the list is empty, copy this into here because the sum is empty and the middle one is the accumulator, which has a value. So put the value into the accumulator into the answer. Well, I'll show you how it works in a bit. So right now I'm just telling you what all the different parts do. So the recursive step, it splits the list into a head and tail. It takes an accumulator as input and returns the sum as output eventually. Um, what it does is it makes a new accumulator. It says new accumulator is accumulator. So our progress so far, our new progress is progress so far plus the head, so the new value, and then call the accumulator function again with the new accumulator and still an empty list for the an empty variable for the sum. Okay, so that's what other parts do. So how does it actually work? Well, we're gonna go through an example again. Once again, step by step, right? So step one is we call the function. This is our initial call. It says I want to add 1 to 3. Please return it to me in X. And um, the only thing it can match with is this first one because it has two variables and it has the same name. So that's the only thing it can match with. And what it does, the only thing it does is call another query with the accumulator. So this is this step where it initializes the accumulator. So that's what it does. We need again a subquery. So this is not recursion yet, but this is going to be our initial recursion. So it calls the function with accumulator 0, empty variable, and the list. And it's going to try to answer this query. Well, is it the base case? It is not the base case. Um, because it's not an empty list yet. So it's going to go into the recursive call. By the way, this looks like two rules, but that's because it's just a new line. So yeah, because it was way too big to put on one half of the slide. Um, so head contains 1, tail contains 2, 3, accumulator contains 0, because that's where we start at. Sum is empty. First thing it does is it makes a new accumulator. That's a new accumulator is accumulator, which is 0 plus head. So the new accumulator is 1. And then it calls another query. The query will be um, sum A with the tail. So we make the list smaller. The new accumulator. So now the accumulator is 1 and still an empty variable for the sum. All right. So um, these are all the calls it ends up making. I'm going through it a bit faster this time. So for example, if we look at this one, same thing, right? So the head is once again 2. Well, not once again, but the head is 2 this time. The tail is 3. Um, the accumulator is 1. That's our progress so far. Once we're on the second step, the progress we've made so far is that the accumulator contains 1. Our new accumulator is 1 plus the head. Um, and then we do a new call where we say some A, tail, the new accumulator, and an empty variable. I have a question in the chat. Why is there the X if it stays empty? Well, that's a good question. You see, once we get to the base case, we're supposed to stop the recursion. The um, problem is that our accumulator is now full, but our output variable is not. So we want our result to be in the output variable, not in the accumulator. So how do we move the answer from our accumulator to our output variable? Well, that's what the base case does. So in the base case, the accumulator, so this one is 6, and this one is empty. But they both need to be the same because they have the same name. So that's where prolog unification, or I don't know if it's unification, but because we're not using an equal sign, but that's where prolog tries to make it work. So these two both have the same name, but they have different values. But this one is an empty variable. So we can say x equals 6. So what we do is we copy our answer from the accumulator to the output variable. So x equals 6. And now we return the answer everywhere down the stack. So we end up returning 6 everywhere, including to our final step, this is our final answer, x equals 6. Now I imagine it does go back, but under the hood it's different. So under the hood is more efficient. I don't know exactly how it works. You guys don't need to know how that exactly works either. But um yeah. So um a question I imagine you guys might have is, why do you need another variable to use as accumulator? Why can't you just why can't you just set the output variable to 0? Well, because if we set the output variable to 0, we're not passing an empty variable. And if we're not passing an empty variable, it will not return an answer. Because for the query to work, we need to give it an empty variable so it can instantiate it with the answer. While if we ask sum 1, 2, 3, and then say 0, as in start at 0, it'll say false, or more likely error, because the sum of 1, 2, 3 is not equal to 0. And that's why you need an accumulator. Okay. Um, on the next slide, we have another task. This one is also again for home, for after this, I mean. Any questions about this? This is just about the um, this is all you need to know about recursion. So if you practice this, go through the examples again. Um, yeah, if you practice this and you manage to get the hang of it, of making these things, then you'll be fine for the exam. So for today, after this session, I advise you guys try to do the tasks on the slides. They're not on the level of the exam, so they're good to start with. And go through these examples again. So make your own examples, right? So ask, just query, make a query and pretend to be the Prolog um, program and just solve these things by hand. So the exam is more difficult than this. Yeah, so on the exam, the recursive rules that you will be working with will be slightly more complicated. But as far as accumulators and tail recursion and left recursion, this is all the theory and all the concepts you need to know. They'll just be slightly bigger. It becomes way more natural when you practice it a bit. Yeah. So this is definitely impossible to understand without practicing it and without doing it yourself. So that's why I really recommend after the session you guys solve these uh, like use these rules by hand. Another question, can you pass without mastering this? So product programming is not a very large part of the exam. And if you do really well on all the other parts, then you'll pass. So you can pass without knowing how to do recursion. And that's why I'm also not spending half of my time on recursion. So this is all the time we're going to spend on it today. And tomorrow we'll practice writing them a bit. But yeah, I have to make the balance between spending time on something difficult and spending time on something that doesn't isn't worth a lot of points. Any more questions? All right. Guess we can move on. Yeah, so the answers are on the slides. And I'll send the slides afterwards so you guys can practice these. I have a bunch of important concepts on this slide. I believe we handled all of them. Look through it, and if there's one that you forgot or don't understand yet, let me know. After this, we're gonna go to the prologue exam. So we're gonna do exam questions. These we're not gonna go to prologue programming part. So we're the prologue programming, so the recursion we'll do tomorrow. But we're gonna do the basics again. What was floundering again? So floundering was when you use the not something in the beginning of your query, it will try to achieve your subgoal. And if it achieves the subgoal, then it will return false, even though your intention was to find an alternative to this subgoal. Yeah. So like where when using not, it will always return false instead of actually doing what you wanted to do. Don't really have time to explain it again, so it's best if you afterwards look at the slides from yesterday. And if you don't understand the slides from yesterday anymore, then ask in the WhatsApp chat, and I'll send an explanation on there. Don't really have the time to go through the entire thing again today. All right. Um, yeah. So after this, we're gonna do the prologue exam, the basics parts. Um, but first, we're gonna take a break. What time is it? Oh, it's already 7. Right. So let's take a break until 20. All right. So break until 10. Or is it already 11? It's already 11, isn't it? I'll leave the presentation on this slide so you can look through these once again during the break. If there are any questions or comments, write in the chat and I'll look at it during the break. And I'll see you guys in a bit. Um, okay, yeah, well, I've already said it. Exam questions. So these are all from the previous exam, not the practice exam, but the actual exam. So the first question is, what would Prolog do? So what are the answers that Prolog would give? We've already extensively practiced this yesterday, so I don't expect it to be a huge problem. All right, I'm already seeing answers. Yeah, so type your answer in the chat. Um, that's all I have to say about it. If there's any questions, if you don't understand one of them, let me know. Maybe type all the answers in one message and wait a bit so everyone has the time to look at it because they're all on one slide. And again, if there's any questions, type in the chats or unmute, whatever. Right, so you guys got the first 2 correct, that's for sure. Any takers for the third one? All right, first one is false, of course. Um, so remember, um, succeeding to instantiate something is the same as true. So not means d- the not asks, did you succeed here, yes or no? And if the answer is yes, I succeeded, then it returns a false. All right, and the second one, let me just while you guys are figuring it out, I'm gonna start at the first one explaining it. So the first one is just unification. So it checks, do they have the same name? Does the outer function have the same name? Does it have um the same amount of arguments? And the last condition was, does instantiation succeed? It does because there's no conflict. It instantiates capital A to small b and capital B to small a, and that's what it returns because you gave it empty variables. For the second one, it's uh, unification again. So while they don't while they don't have an fact that holds the arguments, the plus can also kind of have arguments, right? Because a plus has a argument on the left and argument on the right. So they have the same function, basically, the same format. So Prolog can unify x to 23 and y to 8. The third one, like I said, a equals 4. That instantiation succeeds, so it's false because it's a not. The fourth one, does anyone have an idea for the fourth one? I haven't seen an answer in the chat for that one. Error. Yep, error because it's not sufficiently instantiated, because it does not evaluate the left of the is sign. It only evaluates the right and instantiates the left. Fourth one, fifth one, already saw answers in the chat. That's a more correct use of the is sign. Don't think so because it only instantiates the left. And if you put the variable on the right side, it does not instantiate and it will say error. Other questions? The second one was unification. So the plus operator is also kind of like a function with two arguments. So the same conditions apply. So it instantiates x for 23 and y to 8 to make those two things equal to each other. All right, no more questions. Then we can move on to the search question. So the professors have a really nice way of making it confusing, of course. So in Prolog, in under the hood, whenever you have a variable, it gives every variable a different unique name. So for example, the y here is renamed to underscore 23, but it's still the same variable. It just has a different name. So whenever you see 23, that means y. Okay, so this question is about um, I rewrote the question a bit. Specify the query that Prolog will try to match in the left-hand node, the blue box. So what's going on here is you have a query. The query is question mark AY. So it will, of course, match with the only A, which is a rule. And the rule says X is of type A if X is of type X is of type Y, and X is of type Z. So what's going to happen is whatever variable is going to be chosen here needs to have a fact stating all three of those. And what they show here is part of the research of the search tree. So Prolog was in the middle of trying to answer it when they took this picture. What Prolog does is it takes the inputs, it changes the name of the y to 23. It's the same variable, it just changes the name. Then the question becomes this because it is a rule. So if or in order for the left side to be true, so for the head to be, the rule to be true, the body, which is the condition, also needs to be true. Then it instantiates the variable, the y variable, to n, because that is the first step. As you can see here, it first tries to look for a match for this. It finds one here, so it instantiates x or y, whatever you are, into n. That's what it's doing. Now the question is, what is the next step? So there's a query sign in here. So what's the next query? It already instantiated x for n, so it already did this part. What's the next question that it's going to ask? Yeah, so don't overthink it, right? Um, so the correct answer in the chat. And I guess now the question is which one of the two is the correct answer. Anyone else have um have an idea? No? All right. I'll go to the answer. So the answer is um yeah, y is n also y and is n also z. So what happens is when trying to do the rule, um so this is the initial thing, initial query. Um it just has to answer all these questions. It's confusing, that's also already a y in there. But then it first tries to answer this. It finds a match for it here. It instantiates y is n. And then the big question becomes, does that variable work for the rest of the query, of the rule? And that's what it's going to start try to prove next. All right. Questions? If not, let's move on quickly. Um, the next question is, what will become? So the next one would be, yeah. So the next thing it does is try to answer this part, and if it found one, then the next question it will ask is this. All right. So what will be the outcome of the left-hand search branch when it is completely followed? Success, infinite, or failure? So pay attention. It is not. They don't ask what will be the outcome when the search is completed, but only the left-hand search branch. So only this part. From this part on, it will be failure. Yes, and why would it be failure? There is no ZN. There is not. And that's kind of a problem. So why doesn't it just backtrack? Well, it will, but that's not the question. The question is before it backtracks, because this is where the it instantiates. Before it backtracks, it will fail, and that's why it backtracks. All right. So the next question is, what will it do now? What will probably do now? Well, I kind of already answered this one. It will backtrack, right? Again, I'm just gonna wait. Why does it fail? Um, right. So it instantiated um the variable y for n. It then has to make sure that it will try to find an x, y, and a z of n. So like this is one, this is the other, but there's no one for z. So this part fails because it cannot find a match because set and miss is not there. So this part of the branch fails. Why doesn't it just backtrack? Well, that was not the question. The question was in the left-hand search branch. So after it is satiated for n, it will fail. Then it will go back before it's satiated n and choose a different approach. Choose a different satiation. Was that cleared up? Z has the atom P and Y. Only P. So if you follow this by hand, you will find why it fails. Right? Let's continue. Um, I copied this question literally because it was a really difficult question, even though it's not like what they're actually asking is not that hard. Um, so any variable instantiation is specified alongside a search branch when applicable. Give the variable instantiation that applies to the right hand branch in this given search tree, if any. Otherwise, answer with a cross. So what they're asking is, what instantiation will they do in the right branch? So, yep, pretty much correct answer in the chat. So yeah, when you actually like understand what they're trying to ask, it becomes quite easy, right? Anyone not following? Why does it do the intermediate step um, of 23? Uh, I'm not sure why product does that. Probably to avoid having duplicate names. So, like there probably is, like for example, if you do a recursive step, a recursive rule, you'll have multiple queries that use the variable name y. So if they all use the same variable name, then they'll get the values confused. So it translates under the hood, not for us, but under the hood, it translates every variable to a unique number so that it's there's no chance of rules interfering with each other by having the same name for variables, right? Okay, next. No, yeah, this was the answer. Now there's a bunch of true and false questions. These are mostly about on the exam itself, these were just two questions, but I expanded them into multiple questions and made them true or false. These are mostly about concepts, so not necessarily things you have to understand, but just things you have to know. So do this one for yourself. Um, try to write all the do write answers in the chat, but write them all in one message so people have the chance to look at it themselves. And this is just to test your knowledge. See if you know all these concepts. All right, I'm already seeing that in the chat. Anyone else? If not, I'll start going over them. All right. I'm gonna start going over them. So the first one, product search has incompleteness. Uh, this means that it is not always able to find a solution, and this is true. Second one is prolog search always finds a solution if it exists. This is actually what incompleteness means. So this one is false because it's the opposite of the first one. So first one's true, second one's false, but they both mean the same thing. Three, prolog always uses an occurs check. So an occurs check was some measurement to make sure that queries don't end up in an infinite loop without not talking about recursion, but talking about just unification. And the curse check prevents this. And the question is, does Prolog always use it? Some implementations use some forms of occurs checks, but in general, you cannot rely on Prolog always having an occurs check. So no, it does not always use an occurs check. Again, this is the occurs check is not something you need to understand, just something you need to know, and it's also kind of a minor detail of Prolog, honestly. Four, Prolog is a procedural language. This is false. It's declarative. So declarative is languages like Prolog, and procedural is languages like Python. Um, five, Prolog uses def for search. That's true. That's just how it works. See the answers again. Any questions about this? Oops. Hang on. What the fuck? Huh. All right. So seems there is a bit of a mistake in the slides. Some slides went missing. That's okay. We'll catch up on those next time. There was only like two slides left. All right. So no questions about this? That was it for the basics part. So not a lot of questions. Um, but yeah, that's it. There was some. There was like one more question, but we'll do that one next time. I don't know where the slide went. If there are no more further questions, we can move on to the agent and environment theory. So this one will be quite short. Um, but yeah, so part of this course was prologue, and the other part was agents, environments, and Marble. And they are probably very surely going to ask some questions about this theory. So this theory looks a lot like intelligent systems, and it's also not very big, so I'm not going to spend too much time on it. Just some basic refreshers of, yeah, your intelligent systems. So you have the five environment characteristics. You have, right, so every environment has five characteristics, and these are whether it's deterministic or stochastic. So deterministic means you can um, predict what the environment is going to do given an input. Stochastic means there is some element of randomness, so you cannot always completely predict what's going to happen. Discrete or continuous, is there a finite amount of states? So discrete, if you only have, for example, um, 5 different states that the environment can be in, or if you have 25 or 7 or 200, these are all discrete. Continuous is if you can have an infinite amount of states. So by, for example, moving something, um, like in real life, you can move a chair infinitely small, an infinitely small amount. So there are infinite many states. You have single or multi-agents. So this one speaks for itself. Is there only one agent in the environment or multiple? Static and dynamic. Does the environment change without the agent doing anything? So dynamic means the environment can change without user input or without agent input. And the last one, fully or partially observable. So fully observable means the agent can see everything, just like in chess. Partially observable means the agent cannot see everything, like in real life. Any questions about these? Nope. All right. So yeah, like I said, um, repetition from intelligent systems. All right. Next one is percepts. So the way you've already probably worked in Marble for project multi-agent systems is that the agents cannot cannot see everything in the environment probably, or well, what I mean is the agent needs some way to receive information from the environment, and percepts is how that happens. Now, percepts are like events, but if you have done Snake for programming, for Python programming, then you know what an event is. If not, then just forget about it. But yeah, so percepts are bits of information that the environment sends to the agents, but that's not always right. So there's three kinds of percepts. There is a send on change percept. That one only is sent if the situation changes. So like getting an email, you only get a percept about getting an email if you have gotten a new one. And if you have not gotten anything, then you're not getting any percepts. Send always percepts are percepts that are sent continuously. So a system uh, updates, whenever the environment updates, it sends a percept. This is something like time. So whenever you get any information about the environment, you also get the time of how often of what time it is. The last one is not sure why it's not on here. Is the send on start. This one speaks for itself only at the start. So the send on start percepts tell the agent what the environment looks like when the agent first starts. So this happens once before at the beginning of the simulation and then never happens again. Send on start is actually new since Marble is a thing. Last year with Go, uh, send on start didn't exist. Next, an agent can also have effect on the environment. So percepts is how the agent receives information from the environment, and actions is how agents can um, have an effect on the environment. And these can be put into two categories, either instantaneous or durative. So instant actions are actions that are immediately finished. So the point in time where you start an action is the point in time where you already completed an action. Derivative actions are things that are not done instantly. So Derivative actions are actions that are started, then take some time, and then finish. And the effects of this action can only be seen once it is done. And because it takes a while for the action to be complete, there is time between the start and the finish for the action to be interrupted. So environments can actually interrupt agents' actions, and even an agent can interrupt itself by getting user input, for example. And why is this a big deal? Well, there are a couple things that can happen when a derivative action is interrupted. So, for example, if you get another request by a user, for example, while you're doing a derivative action, then depending on how the bot is programmed, it can deal with it in multiple ways. So either the request is ignored, so the new request is ignored and it continues doing this derivative action, um, or the request overrides the current action, so it stops doing the derivative action, meaning it fails, and it does the new action instead. Or the last one, the request does not interfere with the original action, and both are done in parallel. This one is most intuitive when looking at, for example, video games, where you can walk and look and rotate at the same time. So some bots can do multiple things at the same time, and in that case, derivative actions are not um, interrupted. So it is very important that derivative actions are monitored in case something goes wrong, because they can be interrupted, and you need a way to deal with that. Any questions so far? Like I said, this theory is not very difficult. Just make sure you know all these concepts, basically. And this is more memorization than understanding. No questions then? All right. Um, right. So this part was a bit shorter than I expected. Um, I expected this part to take more time, but that was already it for the exam and the theory. So I suggest we just take a quick 10-minute break and then do marble afterwards. And after marble, then we'll be done for today. All right. So we'll continue um, a bit after 12. Just taking it easy after recursion. So yeah, I'll see you guys in a bit. Everyone back? All right. So, now we're going to talk about the Marble basics. I broke up Marble into basics and advanced, but there's not a whole lot of advanced. So, the advanced next time will be mostly concerned about how to deal with the exam. And today we're going to talk about how Marble actually works. Um, so yeah, let's first set the stage. So we're considering the following scenario. We have a vacuum cleaner bot that we want to program. That's going to be our bot. That's going to be our agents. The environment is going to be real life. We consider anything we can program an agent. So the bot is going to be our agent. Um, the place is going to vacuum. It's just going to be a family house. We're not really concerned with what kind of house. And we're going to assume it is an advanced system that has cameras everywhere to help the agent out. So let's first take a look at what the properties are of this environment. So the typical characteristics of the environment, and it's up to you guys to answer. Is it deterministic or stochastic? And is it discrete or continuous? So this vacuum cleaner bot, what is the environment like? All right, one answer in the chat. Does everyone agree? Or is anyone who has a different uh, idea? Yep. So it is actually stochastic because it is real life. So there's no real way to predict what's going to happen. It's mostly random. That is until we figure out quantum mechanics or whatever. Stochastic means random. Deterministic means not random. You can uh, predict everything. Discrete or continuous? Well, continuous because you won't believe the places that's gonna hide. So there's no way to quantify every centimeter that a room can be um yeah that furniture can be in a room or that dust can be in different places. So in real life, it's stochastic and continuous, and if it's real life, it's almost always this way. Other characteristics is it multi or single agent, fully or partially observable, and static or dynamic. All right, so uh, seeing some different answers. Why do you guys think it's partially observable? That's what I'm curious about. It doesn't see all the rooms all the time. All right, I get the rationale there. Um, all right, so these characteristics can sometimes be debatable. So, uh, this is how I interpreted it. So it's single agent because there's only one cleaner bot, and we consider it only the things we can program to be agents, so we don't consider the humans to be agents. Fully or partially observable, I figured it would be fully because there would be cameras everywhere. Of course, you could argue that it's only partially observable because you can't see below furniture. Um, and that would be a good point. Um, but yeah, this is just an example I made up, and it will be a bit more clear cut when on the exam itself. But yeah, so I would say fully because it's icograms everywhere. That was my intention at least. But you can also argue that because real life you cannot see in every corner. Static or dynamic? Well, dynamic because the pesky humans might move furniture around while the agent is not doing anything. So then the environment changes while without the agent doing any actions, and that makes it dynamic. So questions about this? Don't think so, but yeah, type in the chat if you do have them. So quick refresher from the lectures, not from this course yet. What are the three abilities of an agent? So what's that Marble makes possible? Does anyone know these from the lectures, or I wouldn't know, but maybe you guys know, right? It perceives. All right, well, let's take a look at what they are. Yeah, I'm also tired. These sessions are quite early for me. Let's see. What are the abilities of the agents as defined by the professors? So the first is event processing, which enables it to update its state using the events it receives. So basically, the ability to have percepts. That is event processing. That's one of the characteristics. The second is representing information. So um, every agent in Marble has a representation of its environment. It has a knowledge base in Prolog that has information about the environment, and this is not connected to the environment itself. This is purely its own knowledge base. And the last one is decision making. So based on percepts and based on its own representation of um, the environment, so based on what it knows about the environment, it can make decisions. Um, I'm not sure about communication. It was not. They did not mention communication, so I'm guessing it's not one of the abilities that they don't see it as an ability. Uh, yeah, that's the three abilities. So that's what Marble makes possible. So how does Marble make it possible? Well, it uses it using multiple files with different purposes. So you have three different file types. You have the prolog file, the mass2g file, and the mod2g file. This will probably give you guys a lot of flashbacks to Project Multi-Agent Systems. The prolog files are meant to represent the knowledge of the agent. So basically the prolog files contain the knowledge base. As we've seen while programming in Prolog, we always have a knowledge base in which we put our rules and in which we put our facts. Then we have the mass2g file. This one is not very important for programming the agent itself, but it's what it does is it launches the agent, it connects it to the environment, and it opens percept channels. So the mass2g file just sets up the agent. The mod2g files are files that are actually used for decision making. So yeah, So these contain all the if statements and contain all the um, actions that it's that the agent is able to take. So these are the file types, but there's also the actual files themselves. So so there's usually depending on which agents you're using, there's one or multiple PL files. So on the exam, you'll probably just have one. Um, During project multi-agent systems, we of course had multiple. We have the object.masterg. So object is the name of the agent. Um, that's it's always only one masterg file because the masterg file is like the um, yeah, the parent of the entire folder. So if you want to import a folder, you also use the masterg file. There's an object init file, so mod2g file. That's the um, those are all it contains all the actions that are used that are performed when the agent starts at first. So it's always the name of the agent and then init, and that's the code that's used for when starting the agents. It's used once, never again. Then you have um, the normal mod2g file, so the agent name mod2g file. You can have multiple of these, but you have to import them all using master-g. These contain all the decisions and taking actions, like I said. You can have one, you can have multiple. You'll probably just have one on the exam. Last year with Go, we had multiple, so it might differ. Questions about what these files are for? I'm going to go through each one of them in a bit. Right? No questions? Then we shall continue. So, let's start with the prologue file. The prologue file is the knowledge base of the agents, and it contains three types of knowledge. Usually at the top, you have the dynamic predicates. So the dynamic predicates are bits or facts or rules or knowledge that the agent can insert and remove from the knowledge base while running. So that's why it's called dynamic. They can be added and removed while the agent is running. The way you define them is by using the predicate name, like position, state, alive, and very importantly, you use the forward slash number to indicate how many arguments it takes. We've seen this one before when writing down um, on paper what the rule is supposed to be, but in Marble, you actually have to use it in the code itself. Then you have the normal facts, so the ones you define just like you would do with the normal program. These are used as constants because these cannot be added or removed while the age is running. They have to be changed before the age starts. So these are used for constants, variables that you don't assume will change. I haven't looked at the examples yet, but the dynamic examples are position, state, alive. So these are all things you can change. Of course, the position changes, so you should put it in dynamic so that you can change your position while you're running. But things like the layout of the house, well, depending on how you set up your program, you could put those as constants. So you might already know what kind of house the bot is going to operate in because it always operates in the same house. So you would define the um you would define the what's it called? The layout of the house as constants. Third type is rules. Um just like in a normal prolog file, you can have rules as well, and these rules are usually used as utility functions. So for example, maybe you need a function that uh, calculates an average number or something. So you would put it as a rule in your prolog file, so you can always access the average number when you're doing any code, any actions for the bot. Questions about this? This is quite a long bit of theory before we actually get to the examples. All right. So, or not, maybe we just immediately go to a task. Forgot about that. So let's make a prolog file, shall we? So we have four things we need to define in the prolog file. The first is the obstacle predicate, which has an x and a y coordinate. Second is the position of the bot, which has an x and a y coordinate. Third is the rooms of the house, which can change per house and are defined by the coordinates of the door, as well as whether they are dirty or not. So this time we're actually going to make the layout of the house dynamic because let's say we want to be able to make the bot um, adapt to every house it goes to, then we want the rooms of the house to be able to change. Fourth is the predicate for the charging station, which is always on the coordinates 0, comma 0 or 0, yeah, 0, comma 0. So the question to you guys is make a prolog file or yeah, define all these predicates in the prolog file. How would you write those? Hope you guys haven't fallen asleep in the meantime. Repeat the question, sure. The question was, can you guys define these four things in the prolog file? So we have these four, yeah, these four predicates that we want to have, and we have to define our knowledge base in the prolog file. So yeah, all right. I'm already seeing something in the chat for the first one. However, these are not rules. All right. Okay, so you guys have the obstacle. What about the position of the bot? XY as well. And uh yeah, the rules of the house. All right, so one thing I would like to say while you guys are looking at this, oops, hang on. So the thing is, if you go back to the previous slide, the way you make dynamic predicates is by using the keyword dynamic. So everything after this, after this These are all defined as dynamic, and these normal facts are all constants. So if we look at the obstacle predicates, we have the x and the y coordinates, obstacles can move around because the humans might move them around. So the obstacles are dynamic. So the way we would actually make them is by using the dynamic keyword and say obstacle slash 2. And the reason for this is we don't know before starting the bot where the obstacles are. We want the bot to hear from the environment while running where the obstacles are, which means that the uh, knowledge base has to be updated while running. And any predicates that you want to update while running need to be defined in this list of dynamic. So we can add a comma here to add another predicate, and we can say, for example, position slash 2. So then what would rooms be? Because the rooms can also change per house. So let's say they are dynamic. How will we define the rooms? Rooms 1. All right. However, they have the coordinates of the door, which is the x, y, as well as whether they are dirty or not. So how many arguments does it have? Yep, rooms slash free. Or room without the S, I guess. Now, if it's a bit vague, that does have a reason. It's because these kind of programs are um, like these. There's not a single way to solve a problem or to define something. Um, because like there's multiple ways to program this agent. So depending on how the agent is set up, you'll be handling it a different way. Like I said on the previous slide, the rooms may be predefined as constants, or they may be defined while the agent is running. It just depends. So whether you got it as at the right here doesn't matter. What matters is that you understand the syntax and the idea of what I'm doing here. So as long as you guys understand that, then that's fine. Don't worry about if you got these specific ones correct or not. We'll talk about how to deal with the exam next time. For now, just as long as you understand how the file works. So the predicate for the charging station is always on the coordinates 0, 0. So this one can be a constant. We say charging station 0, comma 0. And this can be an constant because it's going to stay the same wherever we go. All right. So yeah, this is solutions again. Now let's look at the percepts. So in the master.g file, you have to open the channels for percepts because the agent is not able to just receive any percept. You have to tell it what percepts to expect. Now, because there's three types of percepts, there's also three keywords for opening the channels for them. So in the master.g file, you might be asking where in the master.g file. Well, you don't the place they will indicate where you need to put it during the exam. So because they don't actually expect you to understand the entire master.g file. Um, so the way you create a channel is by using the correct keyword. So to use send on start, we use the add keyword. For the send on change, we use update. And for the send always, we use replace. Then the name of the predicate that you're percepting and the slash n for Yeah, for how many predicates it takes. So imagine we have a uh well, okay, I wasn't say that example, but I need to find an example that's not uh yeah, that's not on the next slide. So imagine we have our position, and on starts we hear what position we have from the environment. We don't know where the humans put us down before they start the bolt. So then we would say in the master.g file, add position slash 2. When doing this, it's also important to make sure that whatever predicate you're using here is also defined in the prolog file as a dynamic, because any percepts need to be in the prolog file as dynamic, because these are things that predicates that you are adding and removing while the bond is running. So then the task for you guys is add two channels, add the channels for two percepts, one for a start percept for the layout of the house, the rooms, and on change percept for the obstacles. In this case, they're both already defined as dynamic, so we don't have to do it again. But yeah, add the channels for these two percepts. If you guys remember, we have add, update, and replace as the keywords for send on start, send on change, and send always. So how would you guys add the channels here? All right. Are you guys getting tired by any chance? All right. I'm going fairly quickly. All right. Okay. I'll try to slow down then. It's kind of difficult to gauge these kind of things. All right. So what are we looking at? We have a send on start percept. Yeah, hang on. So I have a send on start percept for layout of the house and a send on change percept for the obstacles. We go back. Send on start is add, send on change is update, and send always is replace. I'm just gonna remove these yellow markings because they're kind of annoying. Add room 2, update obstacle 2. All right, so almost correct because the rooms actually have 3 arguments. So indeed, add room 3, update obstacle 2. Yeah, you guys can ask, I think, Madalif or Mara for the recording. I don't have them, but it is being recorded. Okay, so that's how to add the percepts. Um, Next we will look at the rules. Um, Unless there are any questions still for the previous one. Not trying to go too fast. No? Okay. So let's go to the rules next. Um, so the Moto-G files have rules as well, just like the Prolog files, except Moto-G file rules are a bit different. So Marble rules are a little different from Prolog rules, in the sense that they actually start with a condition, so they don't have heads and bodies. They have conditions and actions. They're actually basically if statements. So um, they always start with a condition. The condition is used in to retrieve the information that you want to use using instantiation and to check if the condition is true. Uh, I'll show what that means in a bit. In the condition, terms are separated with commas. So you have an if statement. If condition, then you have after the then keyword you have actions, and these actions are what to actually do after the condition is uh, considered true. Uh, Actions are, like I said, come after the then and are separated with a plus instead of a comma. We'll look at an example in a bit. We have two kinds. So we have if and then for a single action, and for all do. And uh, the difference between them is that the if statement does it only once, and then uh, the for all do statement goes through all the instantiations for which the condition is true. So it does backtracking and then does all the actions, where an if then just finds one solution and then does the action and does not backtrack. Just drop my pen. It's convenient. Okay. There are also some built-in actions. These are called insert and delete. These are the most important. Insert and delete. So any predicates you put between the parentheses there are things that are either inserted into the knowledge base or removed from the knowledge base. So again, anything you use here must be defined as dynamic in the Prolog file, otherwise you cannot change the knowledge base. So quick summary of the syntax. You have either if or for all do for the condition, and these are then separated by commas, every condition. After the condition is complete, you have the then or do, and then you have actions separated by the plus, and it's important that you always end with a period at the end of your rule, because that is how Prolog works after all. And this is Marble, but Marble is based on Prolog, so it has the same syntax. So an example, this is just a random example with terms I made up, but you have if condition, comma, condition, then delete some information. Within the delete, you can also have commas to delete multiple things. Plus, so another action, insert, and then more stuff. All right. Everyone clear on how to use this syntax? Kind of. All right. So this is the same syntax you would use in Marble, but then again, in Project Multi Ages Systems, I mean. But I realized during this project you had to mostly use the Prolog rules and not really the Marble rules. So I'm guessing you guys don't have a lot of experience actually programming Marble. Uh, Luckily, you don't really need to be very good at it for this exam. So one more thing, um, conditions are used for both checking a condition, but also retrieving information. For example, say I have an if statement, and I want to check if my position is smaller than 5. I can't just say position smaller than 5 because Prolog will ask what the hell is position, right? So if my condition is my x position has to be smaller than 5, the way I would have to do it is, hang on, let me get my pen. I would have to say position, which is a predicate, x, y. So the x and the y are empty. These are empty variables, but because this is like a query. Basically, whatever is between the if and the then. So what comes after the if is basically a query. So if I run this, Prolog will instantiate. It will look into the knowledge base. It will find a predicate for position. It will instantiate x and it will instantiate y. If you don't want it, if you have a bunch of variables, you can also use the anonymous variables for uh, arguments or variables that you don't care about. For example, we don't care about our y coordinates, so we could replace it by a anonymous variable, so we don't have to think of new variable names constantly. And now that we have access to our x position, because we just instantiated x for that number, now we can say x is smaller than 5. So this is how you would check your position, for example. And now we can write then, and now we do some action. So if position x, anonymous variable, and then smaller than 5. Now you're forgetting the x here. X is smaller than 5. Just like when you make rules in just pure Prolog. And then some action, and of course, don't forget the period afterwards. Okay, so that's all fine and well. Let's try putting it to the test. Task. Define a rule that checks if there exists a dirty room, and if so, performs the clean action, which takes no arguments. So when I say clean action, I mean you can just write then clean. Takes no arguments, so you don't even need parentheses. You can add parentheses, but you don't need to. So if you guys remember, the room predicates, we have it in our dynamic. It contains an x, a y, and whether it's dirty or not. Any takers? We're almost done, by the way, for today. So just this final 15 minutes. Final, like 4 slides, I think. All right, very nice. Um, okay, so Storm has a pretty good answer. Mariette is almost, but you're using the is, which is for which evaluates the right side, but the right side is a string. I don't know how is would handle that, so I would not use the is word here, but just an equal sign, maybe a double equal sign. However, the way I would do it is slightly different. So this is my solution. Um, of course, it also depends on how you say dirty or not dirty. So the way I figured is you would have uh, an atom, either the clean atom, which is a string, or a dirty atom, which is also a string. And you could also say one or zero or true or false, but let's just say that this is how we define the room. We don't care about the x and the y, so you can just put x and y. You can also just put them you just put empty anonymous variables, so both are correct. And by putting dirty straight in here, you're already checking if there exists a room um, without using another what's it called condition afterwards. Because basically the condition is, can you find a match for this? Where the first one is a room where the first one doesn't matter, the second one doesn't matter, but the third one is dirty. You could also instantiate a variable for the third position and then check it. Both work.
Okay, so you don't need to have two conditions if you can have it in one.
In this case, you can have it just one.
Okay.
But like I said, this whole marble things depends a lot on how you make every agent and how you set up your project. So there are multiple ways to do it. Um, so slight addition to this rule. So this time, check if our x position is smaller than the room's x position. So slight addition to this rule. I'll give you guys a moment to try to write it out. All right. Seeing the first uh, answer in the chat already. It's almost correct. See if anyone can find this small correction. No one else? All right. Oh, one person. All right. I think it's time to move on to the answer. So, yep, that is how you guys correctly instantiated our position for this x so that we can actually compare it. So this time we actually make sure to put them in actual variables and not anonymous variables so that we then can then compare them. Only small mistake is we still had to check for dirty because the first part of the task did not change. And then clean. Of course, the focus was this comparison, and you guys handled that pretty well. So, um, yeah, Any more questions about how you make rules? Making rules in this exam is a lot easier than making rules was for the project multi-agent systems because we'll be working with very simple examples during the exam, unlike the huge project that PMAS was about. Um, yeah, so if there are no more questions, uh, this was actually. Oh, yeah, go ahead. I can't really hear your microphone. It's not very loud.
Is it better like this or not?
Yeah, that's a lot better.
Okay, cool. So does the position of the predicate room or the predicate position matter? Where they're placed? So position must be first or not?
No, room can be first as
Uh,
well, but
okay. So what I did here in the last answer is correct then?
yep, the only important thing
Okay.
is that this part does not come before these parts
Yeah. Okay. Yeah.
because otherwise it's not fully
Because
instantiated,
else it's not
etc.
defined, and then it gets an error. It gives an error.
Yeah.
Okay.
So, if there are no other questions, that was actually already it for today. Um, do I have the planning on this slide? Hang on. Yeah, hang on. Oops, where the hell did it go? All right, I'm gonna stop the share then. I accidentally closed the PowerPoint. Jesus. Give me one moment. Where did the Zoom go? There we go. All right. Yeah, just planning first. So we did advanced recursion, prologue exam, agent theory, and the Marble basics. Tomorrow we'll do the rest of Marble. There isn't a whole lot left, but we'll mostly be looking at how to deal with the exam. We're also going to practice recursion a lot and whatever other parts of the exam we haven't done yet. Make sure you guys practice recursion today. So I'll be sending a link for some practice site for practice questions. The practice questions, like the first 10 are doable, but after the first 10 it becomes really advanced. So just look at the first 10 and go through the examples we had today some more. So most important is that you guys just find some rule and then make up a query yourself and work through how the rule is going to compute the answer to the query. So like I did earlier, if I go all the way back, it's a long way. So this part where I go through every um yeah, through how through the query and how the rule handles the query and filling in the variables myself. So the head is 2, the tail is a list of 3, and the accumulator is 1, stuff like that. Doing that first really helps you, and doing it yourself especially. Like I can do it, I can show you, but doing it yourself is way more effective. That will help you understand how recursion works. And once you understand it, you can then start looking at the exercises for writing them yourselves. And when doing recursion exercises, you'll be mostly dealing with ones that have lists. And the one on the exam is also very likely to have a list. So if there are no more questions about plan for that, or questions in general, or remarks, then that is going to be it for today. Go all the way back just to show, hang on, this. So yeah, that was it for today. It seems you guys, I think you guys are all tired by now. Well, it is morning after all. So, but still, good job today, and rest for tomorrow because tomorrow we're gonna do a lot of practice. If you have any more questions, write them in the WhatsApp chats, and I'll see you guys tomorrow.
Thank you.
Yes, you're welcome.